So, hello guys. In this video, I have more worked out examples for you on pure substances, and let's get right to it. This problem it says refrigerant 134A is contained in a piston cylinder device at temperature 1, which is equal to negative 12 degrees Celsius, pressure 1, which is equal to 0.4 megapascals. The fluid is heated isobarically such that V2 is equal to 20 V1. Heat is then added at constant volume until pressure reaches T3 equal 52 degrees Celsius. Calculate H1, H2, H3, and you draw the TV diagram. So this this pure substance is being handled under three different phases. There's phase one, then there's this phase two of isobarically heating it, and there's isocolic heating, this constant volume heating, temperature 3. So we are given two properties. It's temperature, which is negative 12 degrees Celsius, and pressure, which is 0.4 megapascals, which is equivalent to 400 kilopascals. So the first thing we want to do is identify what state, what phase um, this refrigerant is in. And from my previous videos, I told you that it's always more convenient to start off your investigation using the saturation properties. So here we want to use the circulation table, circulated refrigerant 134 temperature table, that's table A11. And we're going to investigate whether at at a temperature of negative 12 degrees Celsius, the circulation temperature pressure is 400 kilopascals, and I see. So from the table here, you say how I already highlighted it for you. So, well, at a temperature of negative 12 degrees Celsius, the circulation pressure is 185.37 kilopascals. That means the pressure we've been given in the question is much greater than the circulation pressure at this temperature. What does that tell you? From the properties of phases, compressed liquid, circulation, circulated mixture, and a superheated mixture, we already know that it's only a compressed liquid will always have a very great pressure that is greater than the circulation pressure at a specific temperature. And that way we already know that this refrigerant at state 1, when its temperature is at negative 12 and pressure is at 400 kilopascals, it's a circulated, it's compressed. Okay, it's compressed. But but we have a problem because from the steam tables, we don't have a compressed liquid table for refrigerant 134A. So what are we going to do? We're going to take the properties at this given temperature, but only the properties of the liquid. Because ideally, since it's compressed, I mean, it lacks the component of vapor. So to get the values of V1 and and H1 and U1, we shall only consider the component of it which is in liquid form, and that is this here and this here. So V1, let me go over that again. Normally, what we would do is after finding out what phase the substance they gave you is in, you would go ahead to use that specific table. So if it was water, we would go to the compressed table, to the compressed water table for water at that temperature. But in this case, we're not doing that because we do not have such a table of a compressed liquid for refrigerant 134A. So what we're going to do, we're going to assume circulation at this temperature, and we're going to use the temperature given us in the question, and we take only the values that lie within the liquid phase, and that's why we have 0.0007499 meters cubed per kilogram, and 35.92 kilojoules per kilogram. So that's the first state. But so the second state, we're told it's heated isobalically. If you're new to physics, isobaric means at a constant temperature, a constant pressure. Sorry. Maybe to help you memorize that, pressure is measured by an instrument called a barometer. So from that barometer, you would get isobaric heating at a constant pressure. That means the pressure that was used in one, at which the liquid was at in one, is the same pressure that they're heating at isobalically. So we're going to maintain P as 400 kilopascals, and we've been taught in the question that V2 is equal to 20 multiplied by V1, which gives you this. So after getting that, we're going to investigate again for circulation using temperature. We're using table A12. Why we're using table A12? Because we have pressure, we don't have temperature. Yeah. So I did not insert the table because the whole idea is once you understand how to use such a table before, you can use it conveniently, even here. So from that table, A12 pressure table, you're going to find that at a pressure of 400 kilopascals, the circulation temperature is equal to 8.91 degrees Celsius. And you can read off the value of the specific volume for the liquid phase and the specific volume for the vapor phase. And what do we find out? We find out that the value of V2, which we calculated, lies between the specific volume of the liquid phase and that of the vapor phase. And that confirms to us that isobaric heating brought about circulation for the refrigerant 134A. And once we do that, we can go ahead and find the value of the quality concept. Why do we go ahead? Because every time you have a circulated mixture, you know that mixture has something to do with the concept. So with a quality concept. So basically you substitute for this formula and you get this as your answer. And from there, you can substitute in this formula here to get the value of enthalpy 2, which is equal to this. So now we go to state 3, where they heated the mixture at constant volume, and they attained a temperature of 52 degrees Celsius. And because we're working at a constant volume, the volume within H2 is the same volume here. So they want us to go ahead and find pressure and enthalpy. The same steps we used in the previous step is what we're going to do here. We're going to investigate for circulation of our 134 at 52 degrees Celsius. So this is right here, and this is what you get. So you want to copy it out, and you compare with the value of V3, and we find out that V3 is greater than Vg. Thus, at 52 degrees Celsius, R became superheated vapor. Why is that so? Because from the knowledge we have, we know that once this is true, it means we are dealing with something that is in vapor phase, okay? It has no component of the liquid. So from that table, you can get the answers. See, table A13. And because the actual value of 52 is not printed on the table, we use something called interpolation. And here, this is how the table looks. You have to extract the values from the table gently and systematically, and you plug them into the table that you've created. Okay, and interpolation works in quite a simple way. You get what is in the middle, you subtract it from what is here, and then you get to divide it with just like it's written here. Okay, in case you have a problem, you can pause and you derive it yourself, and you it will be more easier. Okay, I can promise that. So once you've done that, you get the answers as listed here. Okay, but the question is not done yet. He also told us to draw the TV diagram. And this is the crazy bit you want to pay attention. So the TV diagram will have a temperature on the left axis in degrees centigrade, and we're going to put all the specific properties here: volume, enthalpy, entropy, internal energy, everything. So, well, I want you to give me your head so as I can explain to you what is happening in this diagram. The temperature on negative 12, we found that the pressure that we had been given of 400 kilopascals was too much to exceeded the saturation pressure, and therefore it forced the guardian, the parent. Oh, so sorry for that. Sorry for that. What I was saying is, this is a TV diagram. Okay, it has temperature on your y-axis, and these specific volume, entropy on the x-axis. And this is the dumbbell shape for where this is the saturated liquid line, and this is the superheated vapor line. So at a temperature on negative 12, we're gonna circulate the refrigerant. We only increase its temperature, okay, and up to a temperature of 8.91 degrees Celsius. This is a question from the table. At a pressure of 400 kilopascals, this refrigerant of R134 is secured at this temperature. So from negative 12 to this, we got saturation, and that's why you see this graph here. And this heating was done until we obtained V2, and V2 is right here. And we were taught the final state, which is state 3, was gotten by heating on a constant volume. That means there was no change in volume. So this is V1, V2. Actually, we did miss something out. Here it should be V2 and V3 because it's constant. From here it goes up, but temperature has changed and pressure has changed. That's all how it reference that. And uh, yeah, the solution should basically look like that. And I really did go so fast in this solution. And the best advice I would give is make it a habit to constantly pause the video when you're watching on YouTube, when you're studying on YouTube, and you pray back, reprocess, and get your own paper and rewrite what is on the screen. You know, attempt the questions, and there's one way for sure that can tell you the calculations are going to be easy. So we're going to do the next problem. And let's continue with problem two. And problem two is talking about a rich tank with a volume of 2.5 meters cubed, containing 5 kilograms of saturated liquid vapor mixture of water at 75 degrees Celsius. The water is slowly heated. Determine the temperature at which the water is completely vaporized on the final temperature, the initial and final pressure, and I want us to draw a TV diagram with respect to circulation lines. Alright, it will start by extracting the data that is given in the question, and this time this volume they've given us right here is not the specific volume, but rather it's the total volume because it's about volume of a rich tank, the tank. So you have to represent with capital V, and they've given us Mars, and the mass they've given us is 5 kilograms and is of the circulated liquid vapor. And since talking about a circulated liquid vapor, that means whatever talking about, whatever properties they give us, temperature and pressure is those are the circulation properties. And that means this 75 degrees Celsius is circulation temperature. And yeah, so the first part of the question wants us to find the temperature for when the water will be completely vaporized. And what does that tell us? When the water is completely vaporized, it's on the verge of being superheated vapor. Well, it's still under the dome shape, but it just hit that other boundary line. I can use this diagram to show you. It's somewhere around here. If it closes up to this side, it would be called superheated vapor, but it's still on this line. That means the larger portion of it is in vapor. So that means if you find the specific volume, V, which is equal to 0.5 meters cubed, how do we get this? You divide the total volume with mass. That's why we have mass cubed, meters cubed divided by per kilogram. Divide this by this, and you get this. And logically, if you think about it, this specific volume will also be equal to the specific volume of the vapor phase. We're going to look at that in a while, and you'll see why. Well, the clear reason is because if it's completely vaporized, and that's the specific volume, that means that portion of the liquid is barely zero, so we could clearly assume that the specific volume we have is equal to the specific volume of the vapor phase, and that's what we're going to do. So we use table A4. We try to observe for the investigate for circulation properties. So from table F4, just to extract it for you, we're going to check at 75. I hope everyone by now understands how to find what table they use. In this point, we're using table A4 because they talked about circulated liquid mixture and they gave us temperature. So this is a temperature table for circulated water, and that's what we know from our tables or many tables we have. We can use table A4, and that's why we have it right here. And the pressure at that point is 38.597 kilopascals. So for you go ahead to find today write this for constant volume. Remember, talk about rigid tank. That means it's not changing volume, it's constant. And this is what you just told you. We assume that specific volume of the vapor phase is equal to the specific volume. Why? Because it told us that at this state the stage we're trying to solve for temperature, the all contents within the tank are being vaporized. It means they're in vapor phase. They're not just superheated, but they're somewhere, okay? Any increase in temperature will make it a superheated vapor, but it's not just that, but you get it. In the previous video, we covered the difference between superheated vapor and circulated vapor. Well, I could tell you the difference right now. The difference between circulated vapor and superheated vapor is, for us, circulated vapor is any reduction, any small reduction in its temperature is going to bring about condensation, and we're going to get water again. Okay, but for a superheated vapor is we don't it doesn't depend so greatly on a small reduction in temperature because it's already super hot. But for well, I did cover all this already in some videos, so you not to drag along on this one. I'll recommend you to visit the channel and you look it up, okay? But that's the basic idea for circulated vapor is once you reduce temperature by even just one, we're gonna have condensation and we get a two-phase liquid vapor mixture. But for superheated vapor, once you reduce temperature, we still have superheated because it's a very high temperature, like 300 degrees Celsius already, and temperature is so big to a small reduction is so small compared to the very high temperature which the superheated vapor is at. So for the final state is what we want. The final state must be at higher temperature and pressure. Oh, well, this should be quite obvious. It's at the value of being superheated, so we should expect very high temperatures and pressure. Okay. For someone who has been really following, you should understand why I really did this. But to go over that is again, circulated vapor is at the verge of being superheated. So once you're calculating, you have it in your mind somewhere that I should expect higher temperatures and pressure. Yeah. In the video called dubbed pressure cooker, we did go over that, and that's why I drew this comment. So what do we do now from table A4? Now, if we know it's isolated, we're going to look, because the only properties we have is temperature and pressure, and it's right here. So we're going to look for this value from the table, and we could see it lies somewhere here. And while we're looking for that value, we're trying to look for final pressure. And the only property that is given at that point is this specific volume. This pressure can no longer be of any use to find the final pressure. Why? Because at the final point, the only property that's given is a specific volume. That's why we're going to continue using table A4 because this is a circulated vapor, but we specifically look for this. So this is a harder question. You have to go through a lot of figures and until you find something that's close to this, and that's why we have this. You see, it lies between here and here. So we're going to extract this data and we use interpolation, and that's what we have right here. We took temperature, these two temperatures, and the specific volumes, just like that, and we did interpolation. How do you do interpolation? You get T minus 140, you divide it by 0.5 minus this, and you equate it to 145 minus 140, that's why we have 5 here. You divide it by this minus this. Obviously, this is greater than this, so when you subtract this from this, you're going to get a negative, and that's why we have it here. Even this is greater than this, but we're subtracting this from this, so you're going to get negative, and it's going to cancel out. And from that calculation, you're gonna get 140.68 degrees Celsius. And remember, I asked us to find the final temperature and final initial pressure. So the initial pressure is this one here, because we found that the temperature they gave us, well, the mixture they taught we're talking about is lies within the circulation region. That means whatever pressure corresponds with the temperature they gave us is that pressure which is and this is our pressure. Okay, that's the use of the table in the first place to find the initial pressure. So for one thing you want to know is for once you see a situation somewhere, just know pressure and temperature from the table they must resonate. So that's why we have this conclusion here that the initial pressure is that, and final pressure. To find the final pressure, we're going to use interpretation once more because the temperature we want, the final properties lie within here, in between here. So everything we want to know about the final state in terms of properties, we have to use interpolation. And that's what we're doing right here. So you extract data that we did in the first place and that will appear like this. And once you do your calculations, your pressure is gonna do to look at this 368.89 kilopascals. Well, this makes sense, just like I already told you right here. For the final state, we must expect higher temperature and pressure. Well, it makes sense, right? The initial state was 75 degrees Celsius and at a pressure of 38.597 kilopascals. But look, the final temperature is have increased. It has increased from 75 to 140.68. It's like doubling. Okay, from 75 to 140, that's like double the initial pressure, the initial temperature, and for the pressure, oh my god, from 38 to 368.89 kilopascals. This is like tripling it. It's tripling it, and yeah, that means my comment was true. Superheated vapors and circulated vapors, they exist at very high pressures and very high temperatures, which is opposite to supercooled liquids. For a subcooled or compressed liquid, it appears at such even a greater pressure, like it could even be as greater pressure as this, but the temperature is so low. That's the only difference. Here, the temperature is high and the pressure is also high. Okay, but for a compressed liquid, the pressure is high, but the temperature is low. There's a difference. And you want to know that, okay? It's gonna help you. So, it's a good practice after doing your solutions. You draw something called answers, and you write it there. Make it easy for your teacher, lecturer to mark you easily. Okay? It's a neatness thing, so you can do it. You can leave it out. So they asked us to draw a TV diagram, and it should appear like this. Okay, temperature on your y-axis and specific volume on your x-axis. So from the entire table, from what we've been working with, we were told we have a specific volume 0.5 uh, meters cubed per kilogram, and we knew this was the property of the circular vapor. So we do not push it to the side, we rather push it here, and we said there was a heating at a constant volume. That's why we have this arrow going up until we hit the vaporization line. At this line, the gas is at the threshold of being superheated vapor. So this is a vaporization line. So we started off from here and we got here, then we did everything a constant volume till we got the temperature of this and pressure of that. Meanwhile here, pressure was that and temperature was that, and this is it was being circulated, so you know for sure it began from here. But this should be dotted line because we didn't talk about anything like supercoat or compressed liquid. So everything in the question was given starting from within this region to here, then to that. So your TV diagram should look like this. Okay. Okay. We have another problem, and this is a fill out. So we have to fill out this law, this row, this one, and this one. How many is that? 1, 2, 3, 4. Yeah, we gotta fill out that. So the question is, use the property tables for water. Well, once you see the element being specified, just know they're making life easy for you because now you just know you have to use the water tables. So part one, they've given us a pressure of 0.275 megapascals. Once you convert it to kilopascals, it's 275 kilopascals. Why do we convert it to kilopascals? Because the property tables mostly are in kilopascals, except for our superheated and compressed liquids, where you have to keep it in megapascals. And they give us the enthalpy, specific enthalpy value, which is 1,200 kilojoules per kilogram. So what do we do first? We have pressure and enthalpy, just that. So what do we do? Immediately we investigate for circulation. Well, since we've been given pressure, we have to use table A5, which is a circulated water pressure table. So at 275 kilopascals, the circulation temperature is equal to 130.58 degrees Celsius. The specific enthalpy for the liquid phase is equal to 548.86 kilojoules by kilogram, and the specific enthalpy for the vapor phase is equal to 2720.9 kilojoules per kilogram. So now we're going to compare this value that was being given to these two. So why do we say this value is much greater than this, but this is greater than this? That means this statement is correct. The specific enthalpy of the liquid phase is less than the specific enthalpy, but less than the specific enthalpy of the vapor phase. That means whatever the water was being given lies in the saturated region. So remember, we have to find the quality concept and the specific volume and the temperature. So right away, from this information we have here, we could find the quality concept and temperature. We already have it. Why? Why do you know that you already have temperature? Because we said for circulated water or any other thing, the pressure from the pressure tables must resonate with the temperature. So our temperature is this, and our quality concept, we wanted to subtract this value from this value, and this one here, you will always get it from the tables. This SG minus, well, you could do the subtraction yourself, but it's always given the table by HFG. Next time, do I have a table? Well, I didn't include it, but once you look at your table, Kenley, there's that is available for you. You could you will find there's that F sub H specific enthalpy subscript Fg, and it is equivalent to this minus this, and it gives you this value. This is the table, and once you subtract, you're gonna get this value. So those are the specific volume, and you can get it from this formula. And quick substitution. This value is also given at the table, but if it's not given, you will find the the values for this that resonate with this temperature and pressure, and you do the subtraction, and bingo, you get your answer as this. And they also want the specific internal energy. You also use this formula. We already derived this formula, so I'm not spending a lot of time in very many videos, and we've been using it quite often. In case you have trouble with it, you know, there's a video out there that is explain this, but it should be easy because this FG literally means this here. You just change the properties here, and we're multiplying it by the quality concept. The quality concept has no units, so you do that and you get your answers there. So the question was a fill out question, and once you get your answers, you draw the table again. Okay, it's a neatness. You can do it, you cannot do it. But I said for each column alpha, for each lower arm down with, just fill out the values, you know. So your answer should look like this. So we got a part B of the question, and in part B we're given only a temperature of 250 degrees Celsius and a pressure of 10 kilopascals. Well, investigating this temperature is very high, okay? For normal water is very high, and we should expect a superheated vapor. That's what we should expect. But let's see what the answers turn out to be, because this temperature is super high. Okay, let's see. So far, we have to first investigate for situation. Okay, so at a temperature or at a pressure of 250 degrees Celsius, the pressure is 397, 3,996, 300, 3,976.2 kilopascals. And oh wow, we have a problem. I have a big problem. So, um, you realize that this pressure, well, from what we have said, if this pressure for a compressed liquid, it has, oh wow, yeah, it's superheated, just like I said it. Like I said it, yeah. Superheated, because this temperature is so high. You see, so we have a pressure here. This pressure is greater than this. So we know from our facts that if pressure, saturation pressure at a given temperature is greater than the pressure that was given, I mean it's superheated, you know. So yeah, superheated pressures exist at superheated vapors exist at very high temperatures and high pressures. So if this pressure, if this pressure right here was smaller than the pressure we're given, that would make it a compressed liquid. But the temperature itself already tells us something. This is too much pressure to be for a compressed liquid. So yeah, and if the pressure equals, just like we've been talking about, that's a two-phase mixture. So this is superheated water, and we won't use this table. We just used it to get to know what phase the water we're talking about is in, and we already got in it superheated water. So we're going direct to use table A4, A6, which is superheated water table, and from there we can get the value of enthalpy as 2,977.5 kilojoules per kilogram. And from that same table we get these values specific volume is 224.136 milliliters per kilogram, and internal energy is that. So for this, you realize we didn't have a lot of calculations, but the whole crucial part is on how you do your investigation to get to know what region we're in. Once you mess up, once you fumble there, and you just know you just failed the whole thing. And do I have a curve somewhere? Let me go back to the graph. I want to show you something real quick. Well, I've already showed you before, but I want to do it again. So the quality concept X is only real and has an influence once we're talking about mixtures that lie in under this dumbbell. Yeah, you can anything under this curve, okay? But beyond this curve to these regions, the quality concept does not play any relevance. The reason is stated properly in one of the videos where we did, extracting the actual meaning of the quality concept. That's why here, on our answer, we have quality concept is not applicable because we talk about superheated vapor, and wow, shock. So this is the temperature. This is our table. Okay, yeah. So you have to note that. So part 3, we're given pressure as 2.5 megapascals. This is so a lot of pressure, and I won't be surprised if this is super. Oh wow, yeah, superheated vapor. So investigate for superheated properties right away. Why? Because this is too much pressure for a circulated mixture for water. So that's why we right away go to table A6, and table A6 looks like this. This is temperature, pressure, and I'm not quite sure about this. This could be, I don't know. So we are given an specific internal energy of this. So by interpolation, oh well, why did we come to investigate for circulating properties? Because we're given this too much pressure and this internal energy. And from the superheated tables, we already find this specific temperature. I mean, this pressure. It's right here, printed there. And you can relate that this value lies somewhere in between here. You see, this is a specific internal energy. So you realize you're not in the you're not using the incorrect table. You're right. You're there. So you go ahead, do interpolation, and once you do, we've already gone through a lot of interpolation. You extract these values with the temperature, and you subtract to get this temperature at 49.7 degrees Celsius. And you can say, yo, wow, my answer is correct because if it lies in between here and we have 249.7, that means, yeah, well, it's correct. It's somewhere close to 250. Okay, and again, quality concept is not applicable for a superheated mixture. So we're going to find enthalpy, specific enthalpy, and we also do it by interpolation. Oh, okay. This is enthalpy right here. So the value one lies in between here. So you're going to subtract this from this, and whatever value here from this, you equate from this value minus this, and whatever value you have put here minus this. That's what we have right here. And you will get your value as 2,879.998 kilojoules per kilogram. I missed something here. Can I add it? Yes, I can add it. Wow. So we have 287. So you see, we have gotten a value of 2,879.9998, and you see 88, 80. We are not by love, 79 is almost 80 here. So yeah, we could reckon our answer is yeah, actually And we also want a specific volume, so we also use interpolation again, just like we did over there, and we get an answer of this. And we have to conclude our table again. We put the pressure, temperature, the pressure. We have a not applicable quality concept. We have the specific enthalpy. We have the specific volume. We have the specific internal energy. Yeah. So we got to part four. Part four is giving us a temperature of uh, 100 degrees Celsius and the uh, pressure of 2 megapascals. Well, I can tell you that this is a complex liquid. Why? This temperature for water to exist at 100 degrees Celsius, the pressure must be somewhere between. Oh, wow, yeah, here, this pressure. This is atmospheric pressure. You know, above sea level, one atmosphere. So for water to exist at that temperature at 100 degrees Celsius, this must be the pressure. But now they're telling us the pressure is 2 megapascals. That means since this is greater than this, we have a compressed liquid. Okay, but we have a problem. It's true. What we just said is true. There is a compressed liquid. But from the compressed liquid table, the lowest pressure that is catered for is inclusive on the tables is 5 megapascals. So this 2 megapascals is is so less than 5 megapascals. So what are we going to do? We're going to consider the properties of water from the saturation table at 100 degrees Celsius to find these are the enthalpy, the specific volume, and yeah, you know that. But we shall have it in mind that it's a complex liquid, so we won't have a quality concept. So the table we're going to have down is also going to have not applicable for complex for the quality concept because it's a complex liquid, and we're going to only find its values. So we go ahead use the properties of water at table A4. So I want to go over it again. 2 megapascals is less than 5 megapascals, which is the lowest pressure from the compressed liquid table. Therefore, we're going to consider the saturation properties of water at 100 degrees Celsius from table A4. And that's how we got these properties here. And quality concept is not applicable because we're talking about a compressed liquid. So, but again, we have to find well, actually, that's all we have to do because we've been given temperature and pressure, and it's here. And for your information, if this were to be true, the temperature would have been 212. You see? Yeah. So you conclude by that. So did I draw the TV diagram? Yeah, actually, it's not required, but you will understand it better on a TV. Yeah, yeah. Well, actually, you let me do the explanation. It makes sense right now. So what do we have here? We've been given properties of water at 100 degrees Celsius and a pressure of 2 megapascals. But we know water cannot exist, from the compressed liquid tables, this pressure is so low. So what do? We're going to use the properties of water at 100 degrees Celsius. And what does that technically mean? It means that water was still expanding. You know, the temperature that what was this temperature was still bring about heating to increase all the properties to this temperature here. So this is what if you asked you to draw a PV diagram, this is what you would have. Okay, 100 degrees Celsius, and it lies within the compressed liquid. Okay, but you should know that these values we got here, we got them from a saturation table. But we know at this pressure, water will always get circulated only if we get this temperature. And that's why we draw a curve, hit this line, and the pressure is there. Okay, I hope it makes sense. Yeah, I hope it makes sense to you. But yeah, that's it. And yeah, your table should look like this. Well, this is the last example. I think I should go over the reason again. Uh, the property, once you find the pressure for the compressed liquid is lower than 5 megapascals, it is as if they were trying to ask give you the properties of water before it hit the curve, okay, and then they wanted you to use it to it's like it's telling you water was its temperature was still increasing till it hit that circulation pressure temperature at that pressure. That's what we have right here. Okay, and then all the values read off from here are read from the circulated temperature table at 100 degrees Celsius. So yeah, thanks for watching, and I will compile more videos and more examples and more topics. Yeah, see ya.